Hi there! In the first part I explained what RMS is, how averaging multimeters work, and that they're really only meant for sine waveforms. But in this day and age of pulse width modulation and switch mode power supplies, sine waveforms are becoming the minority. So I thought it might be interesting to investigate what different waveforms do to true RMS and averaging meters. But the math behind it gets pretty dense very quickly. So I thought about a better way and developed a waveform analyzer. And here it is. Yes, it's only a spreadsheet, but it works quite well. And best of all, you can download it free with all the waveforms you are going to see and more from my GitHub page. Link in the description. Using it is quite simple. Let me walk through it. In the first column we have sample. This is just a number going from 0 to 99 and basically determines the resolution of the model. 100 samples should be more than sufficient. The next column is wave. This is where you define the waveform by specifying a positive or negative amplitude that corresponds to the shape of your wave when that sample is taken. The spreadsheet assumes that the 100 samples are one period and the wave repeats after that. So if I start punching in some numbers, you can see that this represents some kind of strange pulse, and it's assumed that it repeats every 100 samples. But of course, nothing stops you in copying the same data and pasting it at 50 like so. And now you have two whole periods within the model. But undoing this and copying it elsewhere instead of exactly halfway means that one period now contains a burst of two of these things followed by a gap. Either way, the model can handle it. You see three traces, and in some instances they are right on top of each other, which makes them hard to distinguish, but they are always there. The yellow trace corresponds to wave and is the waveform we just edited. The red trace is called AC wave and shows the same waveform as the yellow trace, but as if it was coming through a capacitor, thus stripped away of any DC part. The red trace is the wave that your multimeter sees. The blue trace is the red trace after it went through a full bridge rectifier. This is what the averaging meter uses to produce the average. The traces have different width, so we can see them when the traces are on top of each other. With these traces calculated, the spreadsheet can now determine the true RMS the correct way, squaring the amplitude values and summing them up, all done by the built-in SUM_SQ function, then calculating the average and taking the square root of the result. It can also calculate the average value, which is actually the DC part of the waveform. Over on the AC coupled side, these two cells repeat the RMS and average calculation, but of course on the red AC wave instead. So the RMS values here are what your true RMS multimeter would show with this waveform. Since AC wave is of course AC coupled, the average is always 0. So while that calculation seems a bit pointless, it is more a control to see that everything is as it should. Last not least, this cell here calculates the average of the blue AC wave rectified, which of course is not 0. This is the value an averaging multimeter like the RS14 sees, and the value below that is the value it displays after the sine wave based correction factor of 1.111 has been applied. Now, while editing your own fantasy waveform and looking at what True RMS, AC True RMS and averaging meter would do with it is interesting, and if you download the spreadsheet, by all means play around. But first I want to show that it actually works by using some waveform that my function generator can produce. That way we can actually do measurements and compare the result with the calculation of the spreadsheet. Let's start with a humble sine wave just as a confidence test. Now I am rather lazy, and instead of typing in 100 amplitudes of a sine wave, I just added a formula that does the same. This does look a little bit confusing, but it's all to convert the sample value into a 0 to 360 degree number, and then that into radians, because that's what the sine function wants as input. This formula is then simply copied into all 100 entries of the wave and produces the value you see here. Using a formula allows you to add a few luxuries, like changing the amplitude as peak, not peak to peak, and period. But it's best to stay within one period because it gives better resolution. So how does reality match? The scope value for RMS is very close, 1.77. I reduced the meter setup to just 2 to be able to zoom into the displays. On the right, the RS14 representing averaging meters. On the left, the BM869S, a true RMS meter that can also offer AC plus DC. If a wave is symmetrical around 0, just like the sine wave, DC or AC coupling makes no difference. Hence, the calculated RMS values are the same. The true RMS meter is very close, and any discrepancy is probably due to tolerances in the function generator in producing the exact amplitude I dialed in. The RS14 is also close to the predicted value, at least within its specified tolerance. Quite a bit more complicated is the case of the full bridge rectifier. This is a very common waveform encountered in practical or power supplies. Function-wise, this is very easy to generate by simply feeding the sine function from the last model through an abs function before producing the wave sample values. Abs standing for absolute value. So the yellow waveform corresponds to the scope plot. We can quickly change the period to 2 and the resemblance is clear. The red trace of the AC wave is shifted downwards. Again, that corresponds to what the scope shows when selecting AC coupling. The blue trace of the AC wave rectified looks really weird. Out of curiosity, I actually fed the full bridge rectified voltage into an AC coupled full bridge rectifier, and yes, the DC output looks like that. Please disregard the values, I was just checking it for the wave shape. Back to real values. In DC coupled, the scope's RMS and average values are quite close to the calculated ones. The same is true for AC mode. The RMS voltage of 1.56 closely matches the predicted 1.57, and the AC RMS value of 1.557 by the BM869S is also very close. The averaging meter is also reasonably close to its predicted display value of 1.51. Of course, this value is not the true RMS. Scope and both meters show the same DC value, which is slightly too high, again probably due to tolerances in the function generator. The combined AC plus DC value is a good match for the scope's RMS. We already talked about the square wave with 50% duty cycle before, so this one is fast. I just wanted to show how I generated it without typing 100 values. Doing it with the if function here allows changing peak and duty cycle very easily. Looking at the values, the RMS, whether AC or DC coupled, should be 2.5, which is close enough on the scope and the true RMS meter. We already discussed that the averaging meter is showing such a high value because it applies 1.111 correction when it shouldn't. Let's move on to something more interesting. This is a pulse, and the only difference between the previous waveform and this one is that instead of switching between positive and negative amplitudes, this one switches between positive and 0. This waveform is quite important as it's used a lot in pulse width modulation. But since the multimeters are AC coupled anyway, for them this wave looks exactly like the square wave before. You see, for the pulse, the red AC waveform goes from plus 2.5 to minus 2.5. And if I quickly flip back to the square, the red trace does the same, 2.5 to minus 2.5. The only difference is that meters that can do AC plus DC will of course show a higher value because of the additional DC offset. Since we already talked about this waveform with 90% duty cycle, let's try the opposite and use 10% duty cycle. The scope shows the true RMS as 1.59 volts and the DC part as 0.56. AC coupled, the scope AC True RMS is still almost the same, 1.5 volts. This matches the model exactly. The left meter also agrees with that 1.5 AC True RMS, while the averaging meter shows just shy of 1 volt. Again, an almost perfect match to the model. And the AC plus DC meter shows the correct combined RMS of 1.59. The pulse or square wave is a waveform where we can potentially rescue the averaging meter by applying a correction factor. We have already discussed this 1.111 factor in the case of 50% duty cycle. How would that factor look like for other duty cycles? I created this table by running the model for peak pulse or square wave, it doesn't matter which, of 100 volts and changing the duty cycle from 5% to 95%. 100 volts is just an example and the results do not change for other voltages or amps. The factor is the ratio between what the averaging meter displays versus what the true AC RMS actually is. Of course, we see the familiar factor of 1.11 appear at 50%. I found this graph quite interesting. First of all, the blue AC RMS voltage peaks at 50% and drops on either side in a symmetrical pattern. This may be unexpected, but makes sense if you think about it. At 50% duty cycle, the wave is at its most wavy, for lack of a better word. At any other duty cycle, you have longer times where the wave amplitude doesn't change at all, being either longer high or longer low. At the extremes of 0 and 100%, it does not change at all and we have DC. That's why the AC voltage will approach 0 in these cases. The displayed average voltage, the green trace, follows this, but because it has already been wrongly multiplied by 1.11, it overshoots the AC RMS. So from about 30 to 70% duty cycle, an averaging meter displays too high. But at higher or lower duty cycles, it drops faster than the AC RMS, so we end up with 52% error or more. Looking at the red arrow trace or the table, if you are content with possibly up to plus minus 11% error, an averaging meter is still usable between 20% and 80% duty cycle, and maybe surprisingly the error is largest at 20%, 50% and 80%, and smaller anywhere in between. So if you're using an averaging meter and faced with a square wave or pulse wave, for example from a pulse width modulation circuit, and you know the duty cycle, you can divide the displayed value by the factor in this table and get the correct true AC RMS from an averaging meter. However, for more exotic waveforms like the next ones, the averaging meter won't be of much help other than showing that some AC is there. To wrap up, a few specials that really test the model and the true RMS capabilities of scope and multimeters. First up, the function generator calls this sine pulse. Mathematically, it's the sine x over x function. It is rather complex to program, and to match the scope picture with a peak centered in the middle, the function treats the sample values as -50 to 50 instead of 0 to 100. A consequence of the math, there's a division by 0, which now happens at sample 50. By definition, for this function, the value at this point is 1, so rather than making it even more complex with ifs to catch this, I simply overrode the function at this point. As a consequence, you can't change the number of periods anymore, but in any case you shouldn't, because you would no longer get values you could compare with the measured data from the function generator. So with that out of the way, the predicted values match the measured data quite well. Overall RMS is 0.55 volts and AC coupled almost the same. The measured values are very close in alignment to the AC coupled mode. DC values also match, and the AC plus DC value of course. Okay, the last model I want to present is proper amplitude modulation. With that I mean that the carrier is higher than the modulating frequency. But since we are using multimeters, I decided to keep the frequency very low so even the RS14 can follow. Therefore, the carrier is just 400 Hz and the modulation 50 Hz. If I set the period to 2, the shape of the yellow trace makes it very clear that in AM the modulation value basically turns the volume knob of the carrier amplitude up and down. You can see the shape of the 50 Hz modulating sine wave in the outline of the yellow wave. The 400 Hz carrier modulated by 50 Hz is implemented as the ratio 8:1 in the formula. There's one more wrinkle, which is this 1/4 offset or 25 of 100 samples. All this does is center the plot nicely in the middle. This is pure eye candy and does not affect the calculation, but why not make it look good? Plotting 2 periods is the limit of 100 sample resolution, and the accuracy is rapidly going downhill. Even at 1 period you can already see the shape of the sine waves are no longer round. Yet despite this, the values delivered by the model check out to a pleasingly high degree. Well, that's it for this video, and I have had quite enough of true RMS and averaging meters. But I encourage you to have a play with the waveform analyzer spreadsheet. While true RMS meters manage to display the correct AC True RMS in all these tests, averaging meters only work correctly for sine waveforms. For square and pulse waveforms, you may be able to correct their readout if you know the duty cycle. That begs the question, why bother with averaging meters at all? First of all, many cheaper digital meters for beginners and probably all analog meters are averaging meters, so they are still around and you may in fact have one. Secondly, having one can be useful if you are servicing older electronics. In many cases, the service manuals were written when averaging meters were the norm and simply assume their use. So check values shown in the service manuals may be in fact wrong when using true RMS because the manual included the error caused by averaging in the target number. So don't throw them out just yet, but be aware of their limitations. Thanks for watching.